Welcome to Cool Fire News, the podcast where we break down complex technical concepts into digestible insights. I'm your host, Siri, and today we're diving into the intricate world of control systems, covering everything from feedback mechanisms to frequency response. Whether you're a student, an engineer, or just curious about how systems work, this episode is packed with essential knowledge. Introduction to control systems. Let's start with the basics. What exactly is a control system? In essence, a control system is a mechanism that manages, commands, directs, or regulates the behavior of other devices or systems. They are ubiquitous, found in everything from household appliances to industrial machinery. Control systems use feedback to ensure that the system behaves as desired, despite external disturbances. Feedback can be either negative or positive. Negative feedback reduces the difference between the desired and actual output, making the system more stable and accurate. Positive feedback, on the other hand, amplifies the deviation, which can be useful in applications like oscillators but may lead to instability if not controlled. Dynamic models of systems. Moving on, let's talk about dynamic models. These models describe how a system evolves over time in response to inputs. They are essential for predicting system behavior and designing controllers. For linear systems, we often use differential equations to describe the dynamics. These equations relate the system's input, output, and internal states. For example, consider a simple mass spring damper system. The dynamic model involves equations that describe the forces acting on the mass, including the spring force, damping force, and external input force. By solving these equations, we can predict how the system will respond over time. Partial fraction expansion. Now, let's delve into partial fraction expansion. This is a technique used to simplify the integration of rational functions. By breaking down a complex fraction into a sum of simpler fractions, we can make the integration process more straightforward. This method is particularly useful when dealing with Laplace transforms in control systems. For example, if you have a function, frac 3x plus 5, x1, x plus 2, you can expand it into frac 1, x1, plus frac 2, x plus 2. This decomposition simplifies the analysis and helps in finding the system's time domain response. Transfer functions. Next, we have transfer functions, a fundamental concept in control systems. A transfer function represents the relationship between the input and output of a linear, time-invariant system in the Laplace domain. It provides a compact way to characterize the system's behavior. For instance, the transfer function of a simple RC low-pass filter might be h(s) equals frac 1 RCs plus 1. This function tells us how the system responds to different frequencies, helping us design and analyze the system's performance. Block diagrams. Block diagrams are another crucial tool in system analysis. They provide a visual representation of a system, showing the flow of signals between different components. Each block represents a functional element, like a controller or a plant, and arrows indicate the direction of signal flow. For example, in a temperature control system, blocks might represent the thermostat, heater, and temperature sensor. The diagram helps engineers understand how these components interact and how changes in one part affect the entire system. Signal flow graphs. Similar to block diagrams, signal flow graphs, SFGs, represent the flow of signals through a system. However, SFGs focus more on the mathematical relationships between system variables. They consist of nodes representing variables and directed branches representing the relationships or transfer functions between these variables. Mason's gain formula is often used with SFGs to find the overall transfer function of the system. This is particularly useful for complex systems with multiple feedback loops and interacting components. Frequency response. Lastly, let's discuss frequency response. This concept describes how a system responds to different frequencies of input signals. It's a critical aspect of system analysis, especially in audio engineering, electronics, and communication systems. Frequency response is typically characterized by two main components: magnitude response and phase response. The magnitude response shows how the amplitude of the output signal varies with frequency, while the phase response shows the phase shift introduced by the system. These responses are often visualized using Bode plots, which help in analyzing the system's stability and performance. For example, a low-pass filter will attenuate high-frequency signals while allowing low-frequency signals to pass through. By examining the frequency response, engineers can determine the filter's cutoff frequency and how effectively it attenuates unwanted frequencies. Conclusion. And that wraps up our deep dive into the world of control systems, from feedback mechanisms to frequency response. Understanding these concepts is crucial for designing and analyzing a wide range of systems, from simple household appliances to complex industrial machinery. If you have any questions or topics you'd like us to explore in future episodes, feel free to reach out. And if you enjoyed this episode, please subscribe and leave a review. Your feedback helps us bring you the content you love. Thanks for tuning in to Cool Fire News. Until next time, keep exploring and stay curious.